As we have discussed in the last lecture regarding the design of compression member using lacing bars as well as the battens, and I told that I will solve a problem or design a column using lacing and battens. Okay, so let us take a problem and see how we can solve a problem using the lacing and battens. Okay. If you are with pen and pencil, then write down the problem, or otherwise just I will simply read the question what I am doing. The question is like, design a built-up column carrying an axial load of 1200 kilonewtons. That means load carrying given in this problem is 1200 kilonewtons. Let us say this is our P value. Given P value is 1200 kilonewtons. Its length is 8 meter. So given length of the column is 8 meter. Okay, N is effectively held in position at both ends and restrained against rotation at one end. Effectively held in position at both ends but restrained against rotation at one end. Held in position at both ends, we can say, but restraining a rotation at one end is a kind of this type of problem. Okay, so this is held in position at both ends, but this end it is restraining a rotation, but this end it is not restraining a rotation. So in this case, what will be the effective length? Effective length will be something like that. Okay, so from here to here, and this value comes how much? L effective, we are interested to know L effective. L effective in this case is equal to, if you remember we have discussed it earlier, is equal to 0. In this case, what is effective length? Effective length LE is equal to 0.8 L. Okay, that's clear. Assume a yield stress of 250 MPa. So here what is given? This Fy is given here. So take Fy is equal to 250 MPa. In addition to that, you use power driven rivets. Now it's depend how we are using, depending on different ways. Suppose in this problem it is asked to design with a power driven rivets. Okay, power driven rivets it is asked, and let us say in the question itself given that use 20 mm die of power driven rivet. Okay, so simple the question is, design a built-up column carrying an axial load of 1200 kilonewton. Its length is 8 meter and it is effectively held in position at both ends and restrained against rotation at one end. Assume a yield stress of 250 MPa. Assume 20 mm die of power driven rivets. Okay, so this is the problem. Let us start the problem. See, initially we do not know whether it is a column which I can use by a single section or I need to use a double section. But since in the problem it is specifically mentioned that you create a built-up section, that means we need to use at least 2 different sections. If it doesn't mention in the question, then we have to check whatever the area we will get. We'll search in the skill table whether is there any section is available with that particular area or not. If it is available, then we may use it, or other way we can go for a built-up sections. Okay, so let us start. So already I have written that effective length in this problem LE is equal to, for this type of support as per the code book it is 0.8 L. Okay, so that is 0.8 into, here the problem length is given 8 meters, so this value is coming out to be 6.4 meter. Okay, so L effective here we got as 6.4 meter. Fine, so one thing is known to us. Okay, next part is, if you just remember the design steps, what I said that when we are using a single section, the load is very less, we'll assume initial permissible compressive stress as around 80 MPa. When we have a higher load, means we are going for a built-up section, we'll assume an initial permissible compressive stress as 110 MPa. So initially we assume permissible compressive stress sigma SC equal to 110 MPa. Fine, this is my initial answer. So now check what is the gross area required. Okay, so gross area required is equal to what? Is equal to given load. Given load is how much? 1200 kilonewtons. So 1200, I am converting into newtons into 10 to the power 3 divided by 110 Newton per MPa, means Newton per mm square. Okay, if we do the calculation, how much it's coming? It's coming around 10909, approximately this much mm square. That means I need, since it is a built up section, so I need at least two section of identical means if you are choosing I section, then both the section to be I section. If you are choosing channel section, then both the section to be channel section. At least I section or channel section will be used for a column. Okay, so that means area required for one section will be half of this. Okay, so maybe you can write down, or otherwise it's fine. Okay, at least these are very close to this value. Okay, let us try with a channel section. Okay, in this problem we will be trying with channel section. Okay, if you go to the steel table, you will find the channel section. Say area required, total area required, I am just writing here, is equal to 10909 mm square. You can write down in terms of mm square, or you can solve it in terms of cm square also. If I write down this value in terms of cm square, then how much it will be? Divided by 100, then means 10 square, 109.09 cm square. Okay, so this is how we can get the area required. Okay, now it is my job, or our job is to go to the steel table and search for two channel sections, and whose combined area will be approximately 109 cm square. Okay, let us see. Let us go to the steel table and find out. If I go to the steel table and search it, I can try with two number of ISMC 350. Okay, if you try with two number of ISMC 350, if you go to the steel table, then you will find their area. While trying this, what we need to also write down their weight. For ISMC 350, what is the weight? Let me check, just give me a moment. For ISMC 350, the weight is 42.7 kg per cm square. Okay, remember, for ISMC 350, its weight is 42.7 kg per cm square, means per cm square its weight. I'm sorry, kg per meter, not area. It is given in terms of length. So 42.1 kg per meter. This is the weight available. Okay, now what we have to do, we have to get the area of this section. If you see the steel table, area of this section ISMC 350 is given, and that is given 54.4 cm square. Okay, so what is the area available? Gross area available is, say area we have available is, we are taking two section, so 2 into 54.4. So how much it is coming? 108.8 cm square. Now it is less than this, but it is very close. So let us see whether we can succeed with this or not. Okay, so these two channels will be placed back to back. Okay, placed back to back, it means this will be placed like that. So this is one channel and another channel will be placed like that. Okay, let us say the clear spacing between these two channels is something called S. We can say, let us say this is the clear spacing between these channels. Okay, now why I am saying that we have to place these two channels in such a way that moment of inertia about y-axis is same as moment of inertia about x-axis. Why we do? We will get an efficient section. That's why we are trying to keep it like that. Moment of inertia about y-axis should be equal to moment of inertia about y-axis. That means radius of gyration about y-axis will be equal to radius of gyration about y-axis. Okay, now if you see this section, if I place this global axis, let us say this is the global axis, okay, and say this is the individual axis of the CG, okay, individual axis of the CG. Now if you look at this, say this is small y with the green line, and say small xs with the green line, okay, small yy and small yy with the green line and small x with the green line. Okay, for the capital global axis, let us say this is capital yy. I am using blue color here. Capital Y, and so this is capital X and capital X. Now if you look at this, that x-axis both directions are overlapping. Okay, that means whatever the moment of inertia about x-axis of individual channel, it will be, and if you take that global together, it will be same because it is crossing the same line. Just it will multiply it, means because since we have 2, so 2 times of whatever the individual x-axis moment of inertia, that will be the moment of inertia about x, capital X. That means what I mean to say, sir, that if I say that moment of inertia about global axis will be simply 2 times of moment of inertia about local axis. Now if you look at this other direction it is not same, because local yy is passing in this direction but global yy is something different. So what will be that? Iyy will be equal to moment of inertia about its own axis. What is that? I small yy plus area. What is that? This is whatever is the area. So this is the area into this distance square. This distance square will be how much? S by 2 plus the CG about this. Let us say the CG about this is CYY. Sorry. Okay. So this will be the moment of inertia about global y-axis. This is the moment of inertia about global axis. Now our objective is to equate these two. If I equate these two, that means Ixx is equal to Iyy. From this equation, if I solve this, because remaining part are known to me, I will be able to know what is the S value. But before knowing the S value, I have to check that whether these two sections are satisfying or not. If these two sections are satisfying our other criteria, then only we go for finding out the S value. Okay, so this is how to do. So that means what I am trying to say is that when moment of inertia are equal, that means the radius of gyration will also be equal. Okay, so how to find out the radius of gyration? That means if I want to say that for this whole section, radius of gyration will also be equal. That means what I mean to say that if these are equal, that means what is there? Rxx must be equal to Ryy. Here see, for the whole section I have to multiply it by 2 because we have this is one direction, another direction. Now if once I equate it, this 2 to get cancelled, that means only individual ixx is enough, individual sections, and only individual section iyy is enough. Similarly, once we equate it, that means what will happen, this r local xx will be equal to, then I have to write down the equation r local y. That is what I mean to say, that both direction the moment of inertia is equal, means radius of gyration are equal. That means for this purpose, what will be the minimum radius of gyration? Because I am interested to find out what is the maximum lambda. So what will be the minimum radius of gyration? Minimum radius of gyration for this combined section or built up section is nothing but same in both direction. That's why I have done all these things. Same in both direction. That means moment of inertia for this built up section will be the rxx of the individual section. So simply what we can write, r minimum is nothing but equal to rxx. Okay, so if you see this individual channel section in the steel table, you will find out the moment of this radius of gyration about xx axis, and this value is given 13.6 mm. Though ryy is less, but we are not using here because we are forcing this section to be same moment of inertia or same radius of gyration in both the direction to get the maximum efficiency of the sections. Okay, so that's why rather than taking the minimum one, we are taking the maximum one, because maximum one is x direction is overlapping with the global x direction. That's why this is the one. So once we know this value, then what our objective? Our objective is now what is the slenderness ratio. Slenderness ratio is denoted by lambda. Okay, so this is the slenderness ratio. Okay, what is slenderness ratio? Slenderness ratio is the effective length divided by minimum radius of gyration. Already we have calculated earlier, effective length is how much? 6.4 meter divided by radius of gyration is how much here? 13.6 centimeter. This is not in millimeter unit. Unit is given to centimeter. We can convert in millimeter also. So this is right here, centimeter. Okay. If you calculate it, this value comes out to be 47.06. So this is the slenderness ratio. Okay, now for this slenderness ratio, I have to go to table number 5.1, or I can use the Rankine equation that is given in the code book to find out what is the actual sigma AC value. Okay, if you go to that steel table, because our lambda is how much? 47.06. 47.06, but in steel table input book table number 5.1, if you refer directly, you cannot get for 47.06. what we have available for 40 and 50. So you have to find out for lambda 40 and for lambda value of 50. Now fy value is given in the code in our problem is 250. So corresponding to 250, if we check that these two values are 139 and 132. So now we have to do the interpolation to find out the value for 47.06. To do the interpolation, what I said, that you first take the minimum value corresponding to the minimum lambda, that is 139, plus now get the difference of these two, whatever be the way you want difference you can take. I am writing like that, 139 minus 132. So divided by the corresponding lambda, that is 40 minus 50. Okay. Now you multiply this. How to multiply this? Multiply this by the remaining. This 139 is for how much? For 40. But our objective is how much? 47.06. So multiply this by 47.06 minus 139. Already I have written for 40. So minus 40. Okay. Calculate this. You will get this value. This value comes out to be 134 MPa. Okay, so what was for 40 it was 139, for 50 it was 132, so for 47.06 it will be in between these two, so we got an value of in between these two, and that is close towards 50. 47 is close towards 50, so we got towards a 50. Fine. What is our next steps? Sigma S is known to us. Now we know the actual cross section that we are going to use. So what we have to check? We have to check that now by this section how much load the section can carry. That is one way. Or other way, what we can do, we can check that how much area actually it will give. Okay, so let us check that how much area actually it will give. Okay, so this we can do in two ways. One is comparing the area, another is comparing the load. So once we know the sigma SE multiplied by the gross area will give me the design load. So, or safe load, let us say I am writing it as a safe load. Safe load is equal to sigma SE 134 Newton, I am writing this way, per millimeter square, multiplied by the gross area of the section. What was the gross area of the section? If you remember it, we have used a section whose area was 54.4 cm square. So 2 into 54.4 cm square, if you want to convert it into millimeter square, then multiplied by 10 square. Okay, now do this calculation. Okay, this will give you in terms of Newton. I am writing in terms of Newton. This is coming out 1457920 Newton. That is 1457.92 kilonewton. Right, so this is more than 1200 kilonewton. So if you say the numerical comparison between the safe load with section we are providing and what is the required was 1200 kilonewton. We have given a section which is giving me a safe load of 1457.92 kilonewton. That means our section is safe. But see, from the economical point of view, this is another crucial part of the design. From the economical point of view, this design is not safe. Means not economical. It is safe but not economical. You cannot give such a huge high value. Okay, so in that case what we need? We need to reduce a cross sectional area, and maybe say that will give another sectional area we have to take, and whose area or whose safe load should be a little bit more than 1200, say within a 10% limit. Then we can say our design will be an economical one. We want safe and economical. This is safe, one can use it, but this design is not economical, so we cannot use it. Okay, so we'll revise the section. So you can write down the comments here. The section is extra safe and uneconomical. Section is extra safe and uneconomical, hence revise the section. Okay, so how to revise the section with a lesser area required. Earlier area was higher, so I am not using that one. So ISMC 350, though it is safe but not economical, so we'll go for another trial. Okay, let us change that. Okay, now what you do, let us try with a section of ISLC 350. ISLC 350. Okay, ISLC 350, its cross sectional area given in the steel table is 49.5 cm square. Okay, we'll check that. So two numbers of, again I am using two numbers of ISLC 350. Cross area is 49.5. Okay, so for 2 ISLC 350, what is the area? that was area required. Okay, so area available is equal to 2 into 49.5. so how much is 99 cm square, or if you want to convert into mm square, then 9900 mm square. Fine. Now what we have to do, we have to find out the R minimum. Is the same steps. Okay, once we have this, now go to the steel table and find out the R minimum. Here again, R minimum is nothing but equal to R axis on the local axis. Okay. So R axis. Okay. So what is the R minimum? If you see the steel table, the R minimum here given is 13.72 cm. Okay. Using that, what we will do, we will find out the lambda value. Lambda value, already we know that this is that effective length is how much? That is written as 6.4 meter divided by 13.72 centimeter, and if you do this, you convert the unit. Okay, this value comes out 46.65. Okay, now again we have to go to the steel table, IS code 800-1984 and find out the sigma SC value. If you go to the code book, you will find the different values of lambda. Okay, what we have? We have lambda value 40 and lambda value 50. For lambda value 40, the corresponding, we have to write down the corresponding was just we have written earlier 139 and this was 132. So if you do the interpolation for this, check it out, this comes out 134.345. okay, so sigma SC is coming out to be 134.345. now what is our next job? Next job is that what is the safe load? What is the safe load? Safe load is equal to 134.345 multiplied by the cross section area. Cross section area was 99 cm square multiplied by 100, so that will give you 9900 mm square. Now you multiply it to get the value of safe load. So this value is coming in terms of kilonewton directly. If I write, it is coming 1330.02 kilonewton. Okay, so our design load was 1200. We got a safe load of 1330 kilonewton. Okay, we can say approximately within very close to the 10%. Okay, so we can say it is a safe design. Okay, so design is safe, we can accept it, right? So once we accept it, then what we have to, now we have to find out what is the spacing between these two. Let us say the spacing between these two is S. So how to find out? We will find out this, because we know that R x-axis is equal to R y-y. It indicates that moment of inertia about x-axis is also equal to moment of inertia about y-y axis. So you have to use that concept to find out the spacing. Okay, so write down. To calculate the spacing of the channel, compare moment of inertia about global axis to moment of inertia about global y-axis. Already earlier I have written the equation. Okay, so simply I am putting the value here. So or otherwise, just for your reference, and quickly write 2 into say I local axis is equal, since we have two channel, I am writing here 2. Now what I have to write? I local YY plus, what is the area of the channel section? So area of the channel section is this multiplied by S by 2 plus, from here to here it is called CY, CG of the channel section in YY direction, this square. Okay, now you put the corresponding value. If you go to the steel table, you will find the corresponding value. 2 into the moment of inertia about x-axis in the code book is given 9330 in cm to the power 4. Okay, in terms of cm, or if you want you can convert in terms of mm also, then it will be 10 to the power 4 mm to the power 4 is equal to 2 into IYY value is available in the code book 396, so into 10 to the power 4 plus, what is the area? Area here we have just written 49.5 cm square. If you want to write millimeter square, multiply it by 100 into S, we do not know, S by 2 plus the CYY value in the code book is given 24.2 mm. Okay, so this square and then this whole bracket. Simplify this equation, solve it, you will get the value of S as very close to 220 mm. Okay, or we can say it is 22 cm. Okay, so this spacing we got S equal to 22 cm. Okay, so with this spacing we got an efficient basic section of built up column. Basically what we did, we have chosen the main member of the column with a proper spacing. Next our job is to design the connectors, design the ties to hold these two channel sections together. That is, we have to design the lacing and we have to design the batten also. Okay, let us do the next part.